So today we're going to talk about RenderScript and kind of take a deep dive through it. My name is Larry Schiefer, and before we get started, I'll tell you a little bit about me. I'm CTO and co-founder of HiQES LLC. We're an engineering consulting firm specializing in mobile and embedded platforms, working from the bootloader all the way up through the application space. I've got over 16 years developing embedded and mobile device software, and extensive experience throughout the software stack. And that includes numerous operating systems, so Linux, Android, Windows, and various RTOSes. I've been working with Android since the first AOSP release and since it was first publicly available. And I've been doing native development and debug along with your typical Java application and framework development even before the NDK was available. I've been the lead architect and developer on 3 custom Android platforms for various customers. And I'm an experienced trainer. I've spoken here at AnDevCon before. I've also developed some training classes for Pluralsight, which is an online training provider. And I also do in-person training for the NewCircle. So today we're going to talk a bit about RenderScript, and we're going to talk about what RenderScript is, and we're also going to talk about what it is not. There are some important things to understand there. We'll go through some typical use cases. Some people have some misconceptions about what RenderScript is, and so I want to kind of go over some of those. And then we're going to talk about the anatomy of a script, basically how you create one and how you actually leverage and use these things. We'll also go through some performance comparisons. I was hoping there would be a projector in here, and unfortunately there's not. I will show a demonstration on a Nexus 7, and unfortunately I'll just have to hold it up for you all to see the pretty screen. But we'll also talk about some performance numbers. And then we're going to go a little bit through some of the debugging and pitfalls you have with dealing with RenderScript. It continues to evolve, so we're going to go through some deprecated and new features that are available in RenderScript. And then what I call the man behind the curtain. So we're going to talk about kind of the underpinnings and do a brief overview of what the system's doing under the hood to actually enable this functionality. We can do some Q&A at the end, but you guys feel free if you've got questions as I go through, just let me know. I'm happy to answer any questions as we go through this. So first thing, what is RenderScript? It's high performance computing. That's what it's intended to be for. It's a customized language. It's based on C99, so it has a very C, C++-like syntax. It's fully parallelized, and it's optimized for hardware as long as the OEM enables that functionality. So it allows you to leverage the capabilities in the end hardware to its fullest. It is target agnostic and extensible, and we'll talk a bit more about that. So a little different than the NDK, where you're building for a specific hardware device, and you have to be very cognizant of what you're deploying upon. With RenderScript, the code that you write is target agnostic. It natively executes on the device. So even though it is target agnostic, you still get the benefits of native code execution. So all that sounds really great, but what is RenderScript not? It's not a general purpose programming language. So it has a very C99-like syntax, but you can't use it for your everyday application development. So therefore, it's not a framework replacement. You couldn't use this, just like you can't use the NDK to replace your typical Java application logic. The same holds true for RenderScript. You can't use it to replace the framework. It's also not an NDK or a JNI replacement. Okay? While it runs at the native level, it's not a full-on replacement, and we'll get into some of that as we go a little further into this. So some typical use cases for RenderScript, and I feel like I'm going really fast, so if anybody has any questions, just slow me down. Okay, image manipulation is a big one. If you look through any of the RenderScript documentation, you're going to see a lot of information in there about manipulating images, and that's usually what the examples are. And in fact, that's what Google uses it for in the latest version of Android. So with KitKat, the image editor or the photo editor that's built into the device is actually using RenderScript under the hood to do the image manipulations for efficiency as well as all the filtering. You can use it for 3D graphics computations, and a lot of folks really thought there'd be a nice tie-in between RenderScript and OpenGL, And in fact, it had kind of gone that way for a while, but as we'll see later, those APIs were deprecated. They found it wasn't a good fit, and it actually has much more use beyond just graphics. So you can actually use it for a lot of other intense computational work. I've seen some posts online of people using RenderScript to do H.264 implementations and their own custom codec implementations, and you absolutely can do that because it's meant for number crunching. So it is all about number crunching. It's all about manipulating data and doing the kinds of things you want to do very, very efficiently on your hardware. So what does the anatomy of a RenderScript look like? Okay, it's integrated with the virtual machine in Android, and the virtual machine is in control and owns all of the memory. So everything that you do memory-wise, it's all managed up in the Java layer. So up here in the framework, your application is going to allocate objects which get put into memory, and it can read and write through them, and then over an interface to the RenderScript, there's a binding so that the RenderScript engine knows how to manipulate this same memory. And it's doing that via some reflected class layers. And it's a very important aspect of this to understand as you see as we'll get into some code here in a little while. So it is a master and slave type relationship where the Java code is the master, and you can call RenderScript via a reflected layer. Now, if you've looked at any of the release notes for the latest KitKat release, I'm sure most people in this room have, they've also opened up RenderScript to be used from the NDK. However, as I'll touch on a little later, the documentation for that is basically nil. There's nothing there. The RenderScript documentation on the Java side is there, but it is a little sparse and it's kind of hard to understand. On the NDK side, there's really none. So you're kind of on your own there. So for most of my talk, I'm going to talk about it all being managed up here in the Java layer. Because really from the NDK layer, I've not had a chance to dive into how that works and how you could actually use it because there literally is nothing to work from. So again, here in the Android framework, you've got your activity, and you're going to have a RenderScript context and then an object which represents your actual RenderScript code. And you're going to call through to the RenderScript runtime by way of this object and this reflection object, which will then actually execute your code within the RenderScript engine running at the native level. So all that sounds great. How do we actually write one of these things? What do we do? Well, the first thing you have to do is you have to declare some special pragmas at the top of the file. Okay, it's one of the first things you have to do. You always declare version 1, and then you've got a pragma which declares your RenderScript. I don't know, can you guys see that all the way in the back? Okay, you can, good. You basically tie in the RenderScript with what the package name is in Java. And that ultimately is what's going to cause the RenderScript compiler to kick out a Java reflection class which belongs inside of this package. So this creates that mapping for you. You can have an optional init function, which we'll talk about that here briefly. And then you have what's called root functions. You can have one or more, especially with the newer versions of Android. Early on, you could only have one. And the root function is really where all of your data comes in and all of your data goes back out. Okay? There are some set forms. And as I found, going through and refreshing my slides in my demo today, it continues to evolve with the API. So in fact, I found that this form here, while it used to work in API level 16 or 17, with the latest set of tools, this form of the root function doesn't work anymore, and it doesn't tell you at build time. It's not until runtime that it just hurls all over you. There are probably some exceptions to that that you can do with some special attributes I'll talk about later. And so that's what this means here, that you get to decide what your root function looks like. So with the newer versions of RenderScript and the newer API levels, you can actually define what you want your root function to be. Previously, it was set. You had to follow a specific form. You can have constants and variables inside of your RenderScript, and you can have other helper functions which work along with your RenderScript. You can also call other scripts, but there are some limitations in what you can do there. So the init function, it's completely optional. It's up to you whether you even want to use this. And it's effectively a constructor. If you've got any type of initialization work that needs to be done before your RenderScript can actually get going and be used, this is the place to do it. It's called one time before your script actually gets executed. It takes no arguments and it gets no return values. So you're not going to get any inputs as part of the init, and it's not something you can trap ahead of time. It's really just for any kind of setup you're going to need before you can get going that's hard-coded. Okay? I touched on the root function before. Now, one thing you'll find in the documentation is the root function is also commonly known as the kernel. And so you'll see a lot of, this word used interchangeably with the kernel function. With the root. This is the main entry point of your script. This is where all the work gets done. And this is where you process your data items. You're going to chew through whatever memory has been shared from the Java space, and you're going to output whatever it is you need to output. It can have multiple forms, like I touched on before. So when RenderScript was first introduced back in Honeycomb, there were some fixed forms that you had to follow. Originally, you had to have exactly 2 arguments, and then it was expanded out. You could have the same 2 in and out arguments, and then you could also pass some user context data to it. Starting with Ice Cream Sandwich in API level 14, the same 2 APIs or forms existed, but now you could also include location information. And you'll see that in the demo here in a little while, where you typically use this for something like a bitmap, where you want to have X and Y coordinates. You want to know where in your data set you are. And there's actually a third form now where you can have a Z coordinate. You can look at it in 3 dimensions. Starting with API level 16, your RenderScript can have a completely custom root function. It's up to you what it looks like. And you can also have more than one, although, as you'll see, that with RenderScript there's lots of caveats, and that is one of them I'll talk about shortly. So constants and variables, these are available only within your script. So if you remember just a minute ago, I mentioned that you can call other scripts from within your script. And that is true, caveats there as well, but you can't access variables in other scripts. From within your RenderScript, you can only touch your variables and your constants. Now, in that reflection layer up in Java, your variables do get automatic accessor methods. So you're going to get a getter and setter. So for example, if I define a 32-bit integer called width in my RenderScript code, I'm automatically going to get Java code, which this is my reflection class here, and we'll go into some of this in a little more detail in a minute. But you can see that I can set the width on it, and I can also get it back out of the RenderScript. So my variables that I've defined in RenderScript automatically get these accessor methods as part of your build process. Structures and pointers are special. You can have structures, you can have memory pointers in your RenderScript, but they are very special. And you have to deal with them accordingly. They can be used directly if they're global within the RenderScript, and they also get accessor methods. And there's a whole separate reflection class that gets created for your structures, and it is kind of complicated. I'm not going to go into a whole lot of detail here. This is one of the areas where there actually is a good amount of documentation and some of the help. Now, memory for pointers are allocated up in Java. Just like everything else, Java side owns the memory on this, and it gets shared down with the RenderScript. So what you do is you bind it. You take a memory allocation up in Java, and you actually bind it over a special call down into your RenderScript so it has access to that memory. Now, your structures can also not nest pointers or arrays. They have to be fairly flat structures. Anybody have any questions so far? I feel like I'm moving about 1,000,000 miles an hour. Yeah. They are very similar. For whatever reason, Google chose to go this path rather than through OpenCL. So OpenCL has not been included in the framework or added as a stable library as part of the NDK. In fact, I believe the person at Google who originally came up with RenderScript and put it in here worked very heavily on OpenCL. So there are a lot of similarities in it. Why they decided to go this route rather than an OpenCL, I couldn't say. So in RenderScript, you can define your own functions. These can be called within your own RenderScript, or you can call them from up in Java. So like everything else, you do get a Java accessor method as part of your automatically generated reflection class. So like the getter and setter, it automatically includes this invoke, and that's how you know you're calling a function. So if I define this in my RenderScript, where I'm simply just taking some data and I'm adding it to some internal data structure in my script, from up in the Java layer, I can actually call that function. I can feed it data from the Java layer. Now this is different than what you would do for your computational piece of this. You wouldn't want to use this for computation. This is really just to be able to push data down into your RenderScript. For it to have, or to invoke some special function in there, possibly for setup or something along those lines. You don't get any return value. Okay, that's why it's important you don't necessarily use this for your computation. You can help augment your computation or feed it some information, but really this should not be the main part of the computation. So calling other scripts. Scripts can call other scripts, as I mentioned before, but you can only call the compute function, the compute kernel, within another script. You can't call, like back on my previous slide where I had my add data function, I couldn't call that from within another RenderScript. You can only call the root or kernel functions. And again, like everything else, all of your RenderScript instances are managed up in the Java side. So even if you're going to call one RenderScript from another RenderScript, your first one has to be fed the information about the second RenderScript from your Java side. So something like a function like we had on the previous slide, you could use to inform your RenderScript of the way or the RenderScript name or handle to call for the other one. This is very useful for built-in intrinsics, and I'll talk about this in a little while with regard to what the platform supports and some of the things that have evolved over time. It's started to support some built-in intrinsics, particularly for image processing. So you can do things like blurring, image data, and that kind of thing. So this is very useful for that, where you can have one script call another script. ScriptGroups are another piece that's been added over the last couple of APIs to RenderScript, and this allows you to chain scripts together. So now instead of one script having to call another script and being aware that it needs to call another script, you can actually set all of this up in Java, and the framework handles it very efficiently for you. So I've talked about the anatomy of a RenderScript and how do you actually write one. Let's talk a little bit about how you call it from the Java side. The first thing you have to do in your activity is you're going to call this static method called create, and you pass it your context. This RenderScript object is really your RenderScript context you're going to use for all of the RenderScript calls as you create your script reflection class. So here I'm going to create my reflection class, and this name will make a little more sense here in a minute, but you can see that the RenderScript context along with resources. This is basically pre-generated version of my script, and I'll talk some more about that here shortly because it's important to understand what that is. But this reflection class, they're all derived from this base script C abstract class. And this basically defines the things that you can normally call in the form that you can call these different classes. You're then going to set up your data on the Java side, and this is done via allocation objects. And this creates the mapping of what your data looks like in Java for what it expects down in the RenderScript. Now you would invoke the script, and you'll see that it uses this for each prefix. So kind of like when you're calling the accessor methods for variables, you get your get and your set. If you want to invoke a function, you get this invoke prefix. Well, here for your root function, you get for each. And it's kind of a funny name, but what that means is it's running your RenderScript in parallel. Okay? It's looping over all of the data you want to feed your script. And so that's what that name really means, is it's for each data point in your allocation, I'm going to call your root function so that you can process that data chunk. So once this returns, you then need to get your data out of the allocation so that you can actually manipulate it up in the Java space now that you've got the results. So you do have to do some marshalling there. So I'll give you a quick demonstration. We're going to do a Mandelbrot fractal and a couple of different implementations of this thing. So let me hop over to some code. So if it becomes too much of an eye chart or it's hard to understand this stuff, you can definitely look at the code on your own. Okay, so the activity for this is pretty simple. I'm not going to really spend a whole lot of time here other than to say it creates a window with no title, so we're going to take up the full screen. And then I create this fractal surface object. And fractal surface is really just a surface view. And this allows me to basically initialize things, and then as the surface is created, as it's changed, I can update it with data from the generator. Okay, it's just a generic way of doing this. The other thing the activity does to make it easy to move between is I hook the key up, key down, the volume keys, and we'll cycle through all my different generators. Okay, so up here in the surface, you'll see I've got a number of generators defined. I'll show you a Java implementation, a multi-threaded Java implementation, RenderScript, a native NDK, and then a multi-threaded native, and we'll look at the performance differences. But I also want to look at the code differences and the complexity differences, because that's one thing that you have to look at as a trade-off here. Okay? Every one of these is a subclass of what I've called Fractal Gen or a Fractal Generator class. It's an abstract class that stores some basic information, and your concrete implementation has to provide two methods. A get name, so it describes it, and I can display it on screen, and then generate. So it takes a bitmap just as an integer array, and it just needs to generate data into that bitmap. Okay? It's a very simple API just for this example. So if we look at the Java version, I'm not going to take any kind of credit for a Mandelbrot algorithm or anything. Pulled it right from Wikipedia. So none of this is going to look really all that complex, but it works and it does a good job. So here in the generate implementation on the Java side, for those that are familiar with Mandelbrot fractals, it should look pretty familiar. For those that aren't, there's plenty of information out there. It's basically going to iterate over every point in your bitmap, and depending on an exit condition for some certain mathematical bounds, or if it hits too many iterations, it'll break out of the loop. And that however many iterations it went through to get to one of those two exit conditions is what determines what we pull from our palette and how we color it. Okay? So it's not overly complex, but it is computationally intensive because it is very iterative in nature. Okay? So you can see it walks through an outer loop, basically the entire height of the image, and then for every pixel in the width of the image on each line, it's going to iteratively do this calculation where it's doing some multiplication and some modulo operations, and ultimately determines its breakout condition by the number of iterations that it's gone through and the maximum number we set, or if it hits a certain stop value. So it's moved beyond a certain point. So once we get the palette index based on the number of iterations it's been through that loop, we set that into the bitmap, and we return when we're done. Okay? So if I fire this up on the Nexus, and I apologize, I forgot to get a projector so that this would be easier to see. So the people in the back, this is probably going to be extremely hard for you to see. It is strapped to landscape mode, so it looks nice and pretty. But you'll see it's rendering for, it's using the Java, and it is done. The screen's kind of dim, so it might be kind of hard to see. And it is displaying some information about how long it took to do the computation. Okay, and I'll go through that here in a second since I can't really show you guys on screen what that looks like. So one of the things you'll see here is as I go through each one of these, the algorithm is exactly the same. There's some slight variations to it, but the code is going to look very, very similar in each of these implementations. So multi-threaded Java, it's again the same algorithm, but now I use a thread pool, and I'm basically going to feed a thread pool with the data to manipulate. However, that could get really expensive and ugly to create objects to feed the thread pool for every pixel in this bitmap. So what I do instead is I feed it a line at a time. I basically tell it, here's your line, do every pixel in this line, and let me know when you're done. Okay? So it sets up the pool, and then once generate is called, remember we're walking line by line, so we're going to feed the thread pool with what I call this new generator task, and I give it the y coordinate and the bitmap to write the results. And now I wait on a semaphore that each of these tasks is going to set when it's done, and I make sure that I get through all the lines before I call it totally complete. And this algorithm should look basically the same, just that we're doing one line at a time. So this is that inner loop that was in the previous version. Let me see if I can adjust the brightness on this to make it a little easier to see. Much better. Okay, so that's the previous version. So now if I go to multi-threaded Java, you can see it comes up significantly faster. Okay? So now let's get to the RenderScript version. That's why you guys are here. You know, who cares about the Java version, right? So we do some initial setup. You'll see, like I mentioned before, we're going to create our RenderScript context, create an instance of our reflection class, and we're going to feed it this resource. And I am going to talk more about this resource here in a little bit. Now, unlike the other Fractal generation implementations, the two Java ones I showed you, excuse me, they automatically get the width and the height from the superclass, but because we have to coordinate with the RenderScript side of things, I need to feed it that information. So the width and the height and the number of iterations, as well as palette data, I need to feed that here in the constructor as I build up the RenderScript. So the palette is a little different as well because it's a giant integer array in the way that I've done this. And so just like the data that I need the computational engine to copy into or to do some number crunching over, I need to feed it this palette data, and the way I'm going to do that is over a memory binding. So if you remember, I mentioned that your memory is managed up in the Java side, and if you need to feed a pointer down to your RenderScript, you have to call a special bind function. This palette, and you'll see this momentarily in the RenderScript, this is a variable that's a pointer. It's a 32-bit integer pointer down in my RenderScript. Okay? So when I call bind here, I'm telling it that this allocation object is an integer array that I've created, and I set the total size and here in the builder, and then I actually copy the raw data that was passed in as part of my construction, and then I bind it, and I tell the RenderScript this is where you can find that data. Okay? So down here in generate, our generate function looks strikingly small on the Java side now. So we create a bitmap object based on the integer. It's a mutable bitmap. Now I create an allocation based on that bitmap, and then I call my for each root. So this is going to call the kernel down in my RenderScript to do what it needs to do over that bitmap. Once it's done, I copy it back out into the bitmap object, get the pixels into my integer array that I ultimately need to pass back to the surface. Okay? So there's a little bit of extra copying going on here. This could probably be a little more efficient than what I'm doing. But for a simple demonstration, I thought it was good enough. So let's look at the RenderScript side of things. Now Eclipse does automatically build this. So if you drop a file in the usual directory layout with your Java code, the Eclipse build engine knows how to pick this up, build the reflection class, and do that. If any of you are IntelliJ users, it's the same thing. It'll pick it up. Now with Android Studio, they did it a little bit different. You don't drop your RenderScript code in here with your Java code. Instead of in the source directory, you're going to have an RS directory. And then you build the same directory structure by package name and drop your RenderScript files in there. Okay, so the build's a little different, and unfortunately, as we'll see here in a little bit with debugging, RenderScript builds along with debugging is not always the most informative thing. So your RenderScript may not build, and it may not give you much of an indication as to why. So if you're playing with Android Studio, I would expect some problems there, or potential problems there. So really quickly, you'll see the same kind of constants that were defined in the Java code, because RenderScript needs to know about them, and then these variables that are defined within the script itself. And there's my palette pointer that I had to bind memory with. And if you look really closely, you'll see that here I'm also using my set accessor methods to set those variables during my initialization. All right, so here in my root function, you can see I'm using the form with the bitmap to take my output data and then my location within the data. This algorithm is probably going to look really old and the same now, since we're looking at the same thing over and over again. But that's important too, because I want you to see that because it has a very C-like syntax, it's basically C99, and even the Java looks very similar to this. It's the same algorithm, it's the same code. Okay? Now the difference here is where on the multi-threaded Java side, I had to break it up. I had to make a choice, right? I break it up by line and I feed it data. Here on the RenderScript side, the RenderScript compute engine's doing that for me. Okay? If it decides to do it by line, by individual pixel, it's up to it. As far as I know, this root function gets called and it's told this is the exact X and Y coordinate you're working with right now. Okay, so however it decides to parallelize that for that hardware is up to it. So my complexity is really not any different than doing it up on the Java side once it's into this implementation. But this is for a single point, right? The one other variation here you'll see, we get our palette index, and now I need to write into the output the alpha, red, green, and blue values based on the palette information. So I shift that around and insert that in there. So if we look at the actual implementation and what it does, so remember this was the last version with Java. We'll look at RenderScript and we're done already. Okay, so it's significantly faster, and we'll look at some of those numbers here in just a second. Anybody have any questions over the RenderScript side of things? Okay. One more real quick, because on the native side, the implementation is multi-threaded or single-threaded, and it's really down in the native code that it makes that decision. So on the Java side, it's really, excuse me, part of our constructor, we tell it whether or not we're going to be multi-threaded and the number of threads. This right here, if you look at the underpinnings of RenderScript and what it does at the platform level, this is more or less exactly what it does for an implementation in the native CPU. So if you're not taking advantage of a GPU on the device and it's just running on, let's say, the ARM core, it tries to figure out the number of available processors, and it spawns that many threads so that it can feed each of those threads. So I do the same exact thing here. Okay? And then we're going to call generate, and down here you'll see that generate is a native method. Okay? So the usual J and I magic ensues. And we'll set up some internal data structures. Similar to the Java side, I basically create a thread pool. However many threads I'm told to make, down here where it's entered in the JNI generate function, I'm going to create a pool, which was that structure up at the top. Just like on the Java side, I create some a mutex to basically know when I'm done. And each of the threads can basically signal me when it says it's done with data so that I can feed it more information. And then we set up width, height, iteration, the same kind of things we had to do on the RenderScript side. We need to coordinate that with the Java side. And then you'll see here, if threads is more than one, we actually spawn off a thread pool, feed it a bunch of data and work, so just like before. And then we wait around for it to be completely finished and make sure that we've made it through. Our total done is our total height. We've made it through every line in our bitmap. Okay? However, if it was just a single thread, we call just a special function internal to the C code that says, do this single threaded. And we're back looking at our same algorithm again. So that's on the single generated version, or I'm sorry, the single threaded version. Here on the multi-threaded side, in our thread, we're feeding it just like on the Java side, line by line. So I need to walk through every pixel on a line, but there's a little more bookkeeping here. You'll see that this is a lot more complex looking than the RenderScript side, because I have to manage the threads. I have to know what data I'm getting. I have to know what work to pull off. I'm just using a simple linked list. Now once I've got through all the bookkeeping and I've pulled something off of my list, I can actually do the work, and I can actually manipulate the data and stick it into my bitmap. Okay? So if we look at the native side, and what it does here, this is going to be single-threaded native. And it happens pretty quick. Okay? Multi-threaded native is really quick. Okay? Any questions over the code, anything I've shown there? Everybody good? All right. So now after all that, everybody's probably going, okay, we flashed a bunch of stuff up on the screen. What does it really mean numbers-wise? All right. I took some averages running on my Nexus 7. It's a little different on different devices because they have different capabilities. So just a straight single-threaded Java, we're about 2.7 seconds to render that image on average. Multi-threaded Java, we dropped to 1.2. So we do see some benefits with multi-threading, as we would expect. Now, RenderScript, we suddenly dropped to 680 milliseconds. So there's a pretty significant boost there. Single-threaded native's about 1.1 seconds, which was actually kind of surprising to me that single-threaded native came out really close to multi-threaded Java. But it's an interesting data point. And then you've got multi-threaded native, which is strikingly close to the RenderScript side. So looking at it graphically, it's smoking fast. So you can see that the RenderScript and the native code are actually really, really close. Okay? And the complexity, in my opinion, was a lot less in terms of writing your code. Any questions over the numbers? All right. So now debugging. It's very limited, okay? If you're used to source level debugging, you're in for a treat. You've got RS debug is about it, okay? And it's really just a very primitive printf, and you can't even really treat it like printf, okay? You don't get variable arguments. You basically get a fixed string and a number of data points that you can output, and that's about it, okay? There's no source level debugging available on this thing. If any of you have worked on other embedded systems, not Android, not working at the Java layer with all these fancy IDEs, you'll probably be right at home here, okay? For those of you who have not, it's a good challenge. Take it up. So sometimes you have to get creative. There are some capabilities in the platform that I haven't talked about. You can send messages up to the Java side. So you could feed the Java side some information, and you could have your own framework, if you will, if you really wanted to spend the time on it. So you could feed your Java code some data and have your Java code be a little, sexier with the way that it output things. But you got to be really careful there. The last thing you'd want to do is maybe set a breakpoint there, lock up your CPU or your GPU. It'd probably be kind of hard to do with the way that the framework tries to parallelize it and keep everything running in the background. But there is some potential there, so be very careful. So some of the built-in features, again, it's all about computation. So you've got standard mathematical functions, trig functions, logarithmic, vector, matrix math. All those capabilities are right there in RenderScript, just like OpenCL. You have a lot of that same capability. Okay, basic drawing functions. So you can do some basic drawing functions within RenderScript right into, say, a bitmap. Now there's some intrinsic scripts, and I touched on this a little bit earlier. You're going to manage these just like your own RenderScript, but they're special objects that you can create that come with the platform. So the form looks a little bit different, but you can effectively treat it just like a RenderScript that you've created. You can call it directly, or you can chain it together with other scripts. The intrinsics tend to be very graphics heavy. Okay? You're going to have a lot of blurs and blends, color matrices, convolve operations, YUV and RGB conversion. Those are all built into the platform and available for you to use. Okay, OpenGL was in for a while, now it's out. I couldn't tell you why they decided to do that, other than I think they tried to maybe, just my speculation, they wanted to emphasize that this is meant for any type of computation you want to do, not just graphics, even though most of the documentation kind of points out a lot of graphics examples. Okay. Now with Android 4.4, it is available in the NDK. I mentioned this earlier. You won't find any documentation on it. If you download the latest NDK, you look in the docs directory, you're going to see a RenderScript subdirectory into there, and you're going to get all excited and go, yay, there's HTML there, and really all it does is point at the header files. So you just kind of have to go spelunking through header files to kind of figure out how it works on the native side. All right, so some trade-offs. Most of you have probably already figured most of this out, but you get big performance gains by using RenderScript. Okay? It's portable. I didn't touch a whole lot on this, but one of the things that if you've ever built something in the NDK, part of your makefile, you have to specify what architecture it's targeting. Okay? So the first version of the native implementation here that I ran on this Nexus, it was dog slow. And I realized it's because I just put ARM architecture instead of ARM v7. Okay? It makes a world of difference in what gets compiled and what's generated there. So with the NDK, you really have to pay attention to what architecture you're targeting, and you've got to build that into your makefiles, and each one of those libraries gets bundled as part of your APK. Here in RenderScript, it's portable. Okay? And I'm going to talk about that because some of you are probably scratching your heads going, how? I'll touch on that here in just a few minutes. It's fully parallelized. So like I mentioned when I was talking about my native implementation, if it's running on the core application processor of your SoC, it tries to figure out how many cores are there and it spawns that many threads to handle it. If it's running and taking advantage of, say, a GPU, it's kind of OEM specific what happens there, but it still fully parallelizes that and tries to leverage what it can out of the hardware. So it leverages the best of what the SoC has to offer. It's a familiar language. Most people are probably used to seeing C or C++. And it can be easier to work with in the NDK for those building purposes, those building reasons. But it is limited. Okay? So some of the cons, you have to deal with the cross-language runtime coordination. If you're already used to dealing with the NDK, this probably isn't a huge hurdle for you. Having to deal with the JNI interface, it simplifies that a little bit, but you still have this cross-language coordination of data. Okay? You got a whole new set of APIs to learn, which in some cases are not documented very well. Poor documentation. I keep emphasizing that because unfortunately it's not gotten any better. It's still really hard to understand some of what's going on in there. And there's poor and limited debug support. It's still changing. Like I mentioned earlier, that root function in my Mandelbrot implementation, I was taking an output pointer and then an X and Y coordinate. The original implementation of that, for those of you who are going to pull from the GitHub repository later, if you go back through my revision history, you'll see that in an older version of this, it actually had an input and an output. And it worked great until I upgraded into the latest tools this morning. Shouldn't have done that. So when I did that, it suddenly barfed all over it, and it really wasn't at build time where it gave me problems. It was at runtime. And So the build worked flawlessly. It had no problems. I stick it on the device. Great, it did the Java run. It did the multi-threaded Java one. Skipped to RenderScript, crashed. Okay, with no explanation of what's going on. Tried to hook up a debugger to it. Debugger doesn't even catch the crash. I mean, it's dead as a doornail. And no information about why that's happening. Luckily, I managed to figure out that it was because they changed that form with the X and Y coordinate. They don't expect an input in that case anymore. So had to modify the code there. So a lot of it's still evolving and it's still changing, so it's a little bit of the Wild West, but you know, it's one of those things you have to weigh as you're deciding whether to do this. The support in Android Studio is a little bit poor and not documented. So like I mentioned before, you have to put your code in a different place than you did traditionally. They've also introduced a support library which takes RenderScript support all the way back to Gingerbread. And unfortunately, that Gingerbread support library will not work with Android Studio. So deprecated APIs, it's really just the OpenGL. So all your mesh, program fragments, all the different things that they had added to RenderScript to take advantage of OpenGL, they've now deprecated, and you're not really supposed to use that anymore. New features. Intrinsics are relatively new. That wasn't in the first version. That came out around API 16, I believe. ScriptGroups, which are pretty cool, but you won't find a whole lot of information on them. Multiple kernel root functions. I mentioned that before. And custom kernel root functions. So you can define what data you want to feed it, and it's completely up to you. Filterscript is another new feature, a new API. I'll touch on that here in a second. And then the support library I just talked about a moment ago, which is available all the way back to Gingerbread. It requires Eclipse or Ant, no Android Studio. I think they're going to change that in the future, but you know, who knows. Especially now with KitKat being focused on lower-end devices and reducing the memory footprint there, there's probably not a huge push to support Gingerbread through the support library, but you know, time will tell. And now you can use it within native code. So most of these changes have just happened since Jelly Bean. Okay, so they're all relatively new things. You can see this continues to evolve. Script groups allow you to chain together. I've mentioned these a couple times over the course of the talk. The reason these are kind of neat is they're more efficient. The RenderScript engine handles all the routing of the data. So instead of you having to call one script, get the data out, call another script, get its data out, or call a script and tell it what other script to call, or have it hard-coded in your code down at the RenderScript level, the RenderScript engine can take care of that for you. Okay? It's touched upon in the docs, but there's really no details. Okay? It requires at least API level 17 for both your minimum and your target. Okay, so 17 or newer. And you're basically going to set up, using this script group builder, a chaining of all these scripts together. Okay, so you basically add your kernels to a group, okay, using an add kernel call, and you pass this kernel ID, and then you add a connection between the kernels in these different scripts. And you're going, whoa, whoa, whoa. We've talked about root functions. We've talked about all kinds of other things. What in the heck is kernel ID? You're not going to find any information about that either. It's an undocumented, reflected method called getKernelID and your specific root function. You have to use a special attribute in your code to define it as a root function. You can't use just the default root. It won't work. It won't automatically generate you one. So, I touch on that here in just a second with this attribute. But once you do that, you can get this kernel ID, and now you can patch these things together. And the connections, there's a couple of different forms. You can add a connection between data types from one script to the other to call the root functions. And then there's also some ability to take one script's output and just feed it right into member data in another script. Okay? This is very handy for intrinsics. So the intrinsic classes, again, they're kind of specialized forms of these, and they hide a lot of the RenderScript functionality. And they have built-in documented methods to get kernels. But really, if you want to bridge together or chain together your scripts, because this is where it gets really confusing, because you really don't know how to get the kernel ID. So custom and multiple kernels, I've touched on this. It's touched on in the docs, but there's very few details about it. And this is that attribute I was telling you about. So you define this in your RenderScript, and that tells the compiler and the engine that this is now your root function. Okay? And it's going to generate multiple for each, and then your root name that you use here. Okay? The compiler errors, if you mess this up, are bizarre. And really kind of hard to understand. Unfortunately, there's not a whole lot of information on that. The multiple root is in concept. It's not in the name. So you're not doing overloaded functions. You can't have one defined as a kernel root that takes these two inputs and then another one that takes a couple of vectors and call them both root. The compiler will say, no, sorry, can't do that. So they have to have unique names. They can't be overloaded names. Now, Filterscript, I just kind of briefly touch on this. This is intended specifically for image processing. So whereas RenderScript is for any type of computation, and the documentation is very image heavy, Filterscript is really what they intend to use for image processing. It's intended to be even more generic. You use an FS extension rather than an RS, but it's basically still RenderScript-like. The built-in types cannot exceed 32 bits, okay, which is a little different than RenderScript because you can have a lot larger bit width. You also have to put a special pragma at the top of your Filterscript, which is telling it to relax the floating point. So you don't have to do full floating point operations. And your inputs and returns cannot use pointers at all. Okay, so it restricts that memory binding. And you have to declare a custom root in your Filterscript. You can no longer depend on the default just root function. All right, so what I call the man behind the curtain. So we talked about it before. The Java virtual machine and RS engine, they coordinate with each other, with the virtual machine being the master and the RenderScript being the slave. So Java reflection classes, and basically it gets compiled into what's called Bitcode for RenderScript. Okay? And here's kind of a flow of what happens. Your RenderScript code goes through what's called LLVM, and you get your reflection class up on the Java side, and then you get this Bitcode resource. Both of those get fed into AAPT to create your APK. Okay, and you get your package. And you're probably scratching your head going, Bitcode? I've heard of bytecode. We talk about Java here in Android all the time. What in the world is Bitcode? Okay, LLVM is another type of virtual machine-like technology, and it outputs optimized bitcode for an LLVM engine. Okay, it's platform agnostic, it's highly optimized, and Android finishes the RenderScript compilation at runtime. So what happens is when your APK gets stuck on one of these devices that supports RenderScript, the first time that it's launched and it needs that resource, the RenderScript piece goes, hold on, I know this is RenderScript and I've got a bitcode resource, because you remember we fed that into the constructor, and if it hasn't ever loaded it before, it goes off and it finishes the compilation and basically takes that bitcode and turns it into native code. So your device has an LLVM compiler actually on it to support RenderScript. And it compiles and links this into machine code for your SoC, and it could be something that's just for like your ARM v7, or something the OEM has provided that knows how to take it on the ARM v7 and communicate with the GPU and feed the GPU data. It's also cached for future use. So this happens the first time you run this RenderScript, and the output of this compilation gets cached, and it's used, the cached version is used as long as you don't update the APK from that point forward. Okay?
Performance hit there?
The first time you run it, sure. Yeah.
If they're going to do anything like they're doing with ART, or maybe ART, the ART install time.
Right, and do it at install time. I have not heard anything. or read anything that says they're going to do something about it. Right now, all the code, basically the first time you instantiate it, it goes out and checks the cache, and if it's not there, it kicks off a build for it behind the scenes. So I don't know what their plans are to not possibly do that at install time. It certainly might help the first time you load something. Okay. In the end, what ends up happening is you get a special shared library that the RenderScript engine that runs as part of your application knows how to link against. And that's how you get that near native performance, or basically native performance. So on the framework side, it's comprised of Java, JNI, and a bunch of native libraries. Okay? And there's a whole slew of them here. You've got the RenderScript piece, you've got the JNI that works in conjunction with that, RenderScript itself, which is all written in C and C++, and then the actual compiler, and then there's this driver piece. Okay, it's primarily all done in native C and C++. So the Java side of this is pretty thin. It pretty much calls down to JNI and calls native code to do all the work. Okay? That's the piece that's very platform specific. So if you pull down AOSP and you look at the source code here, you're going to see an implementation, there's a base implementation that'll be for the application processor that's running Android. OEMs would need to provide their own customized version of this to take advantage of something like a GPU or a DSP or something along those lines. And that's one of the things that they've recently done with KitKat, is made some optimizations here and have tried to work with the OEMs so that the Nexus 4, the Nexus 10, Nexus 7, and Nexus 5 all see some performance gains because they've tried to optimize these and take advantage of the GPUs. So your RenderScript class, if you remember when we walked through code, this is the context for the scripts, and it manages the native threads, which are all done in pthreads, just like I did in native code, to do all the work. Okay? This is also what maintains that RenderScript cache. Okay, so the cache in your application, of compiled code, basically that Bitcode to a native shared library. It's an app private cache that's available just to your application, and it manages native instances of the RenderScript objects. So this script-C class is the base, we talked about this a little bit, of your generated class. It's a subclass of script and base object, and it loads the bitcode and compiles it if needed. So the context manages the cache, and it works in conjunction with the script-C to actually do the compilation if it's needed. The first time it's run, or if you update your APK and that RenderScript resource has changed, it'll recompile it again. Okay, the instance defines an ID for the RenderScript, the context, so there's some coordination going on between these two things. So all of your for each, invoke, get and sep, wrap calls to RenderScript, those are all handled inside of here, down within the framework. So if we look at a diagram of it, you basically have your script-C for your script, which goes into the RenderScript engine, crosses the JNI boundary, and feeds data into worker threads. And that gets passed off to your Bitcode library, which has been compiled to whatever the platform supports, whether it's just the application processor on your SoC or it's taking advantage of a GPU, DSP, whatever. Okay, any questions over all that? That's a great question. I think it's up to the OEM. So if you're going to take advantage of the GPU, the OEM would have to make sure that they provide an implementation to not starve off OpenGL operations or 3D graphics operations, right? I think you'd probably run into the same kind of problem with OpenCL, right? You have to have that kind of coordination and scheduling there, and unfortunately, there's nothing in here that I've seen that lets you tweak or update the way that that behaves. Okay. Now, certainly one potential gotcha that's in here, from what I've seen of the base implementation, which uses the application processor of your SoC, it spawns enough threads to match the number of cores. So there's some potential for starvation there if you're doing a lot of work. And I've not looked close enough at the underpinning. So I kind of touched on it here so you guys get a peek at what's going on with that man behind the curtain. But what is it really doing under there? How is it scheduling those threads? Is it truly just feeding enough, for enough threads to match all the cores? Because if so, yes, you could potentially starve off the system. Any other questions? Okay. So it's a powerful computational framework. It's C99 based, so it's probably going to look familiar to most folks here. Okay. You've got trade-offs versus pure Java and native JNI. Your performance is close to native. It's a little less complex in dealing with JNI, particularly if you're going to do parallel operations. You do have inherent parallel operations on a multi-core device, or even be able to feed to something like a GPU. If you do your own native spin with your own JNI, you've got to manage all of that. Okay, this takes away some of that complexity. It will take advantage of a GPU or a DSP if it's supported by the OEM. Okay. It is device architecture independent because it does finish that compilation once it's run on that specific device. And your debugging is very, very limited. All right. You do have some built-in image processing intrinsics. I would hope that they'll continue to evolve this and possibly provide some more intrinsics based on demand. Right now, the biggest thing we're seeing it in is image processing, and that's what a lot of the documentation focuses on. But you can use it for a lot of other things. And it does continue to evolve, so hopefully it'll continue along that track. You use Java reflection classes to access your native runtime. All right, so here's a bunch of links for you. It has been updated since the conference slides were fed. I made a few tweaks to it. So this copy URL is, you can get this presentation up there, and all of this is up to date on there. The SDK documentation, AOSP source code, and then the GitHub for the Fractal code is down here at the bottom. Anybody have any other questions? All right, thank you for your time.